Good morning, everyone. Is it visible?
Good
Good
morning,
morning,
sir.
sir.
Is it visible?
Yes, sir.
Yes,
Yes,
sir,
sir.
visible.
Okay.
Yes,
sir.
Okay. Okay. Thank you. So today I'd like to discuss about the timing diagram, instruction execution. I have already told you the various instructions, function, different functions. So how this instruction works basically, what according to the time. Okay. So that is the timing diagram, which I need to discuss right now. So so the 8085 that is designed basically to fetch the instruction and which is pointed by the program counter, then it decodes the instructions and then execute the instruction. Okay, so if it is necessary, then further operand fetch means if it is after identifying or interpreting this opcode, which operation is to be performed after decoding this, if it requires to fetch again the data part, means the operand part, that will take place before completing the execution. And all of you know that every instruction has two parts. One is the opcode, another is operand. Opcode means which operation is to be performed. Operation code. For example, move, add, these are opcode. And another part, which is the operand part, that is the data or bytes or the contents of any register. Okay, that is called the operand. So every instruction is opcode and operand. So operand may be given inside the opcode, sometimes based on the addressing mode, based on the function, and sometimes it is specified differently or individual, separately, opcode and operand. So for external uh, to execute, basically to execute a program, 8085 performs various operations such as opcode fetch, operand fetch, and memory read or write, or IO read, IO write. These operations can be performed. So the microprocessor's external communication function that can be divided into these three categories. Number one, memory read or memory write. Number two, IO read or IO write. And number three is interrupt request acknowledge. Interrupt request acknowledge. Okay. So what is timing diagram? Now the timing diagram of an instruction that is obtained by drawing the binary uh, signal levels on the various signals of the 8085, and always it is drawn with respect to the clock input of that microprocessor, and it explains the executions of the instruction using the basic machine cycles of that instruction. So we need to identify, we need to familiar with certain terms, those are related with the timing diagram. Okay, the so some of these terms are like t states, machine cycles, instruction cycles, these. So here the clock signal input is just like a square wave signal. This type of signal is here, and one t state is to be considered from this falling edge of that pulse to the rising edge of the next pulse. So this portion is called one t state. T means the time. Okay, so one t state is this one. Falling edge of this pulse to the rising edge of the next pulse is called the one t state. Okay, so as we know that every microprocessor has its own frequency range, frequency clock frequency is there. So if the clock frequency is 3 megahertz or some other like 2 megahertz or 3 megahertz, whatever, so the time period will be calculated in this way, t equals to 1 by f. So it will be executed within that particular microsecond. Okay, so this is the one t state. This is one t state. Okay, Swarnabo, mute yourself. Swarnabo, mute yourself. Roll number 128. Swarnabo, mute yourself. So there are certain definitions. Okay, all of you must familiar with these definitions first. What are the definitions? Then these terms are very much related to this timing diagram. The first is the instruction cycle. Instruction cycle. So what is instruction cycle? It is the time taken by the processor to complete the execution of an instruction. Complete instruction means move A comma B, that is a complete instruction. MBI A comma 30, that is the complete instruction. JMP 9000, that is the complete instruction. Okay, so don't take any instruction as MVIA. No, it is incomplete instruction. You have to specify the instruction fully. MVIA comma some data byte, any data byte. Suppose 50 is there. Okay, you can't take this one as JMP only. No, JMP 0005. That is the complete instruction. Okay, so it is the time required by time taken by the processor to complete one such complete instruction execution. Okay, and this consists of 1 to 6 machine cycles. It depends on the instruction functions, how many machine cycles will be there. So it may be one machine cycle, maybe two, maybe more than this, up to maximum 6 machine cycles. So the second term, second definition is for machine cycle. Okay, machine cycle. So what is it? It is the time required to complete one operation, either accessing either the memory or an IO device or input output device. Okay, so that is called one machine cycle. It is the time required to complete one operation. It is the time uh, required to complete one operation accessing either the memory or an IO device. So a machine cycle consists of 3 to 6 T states. A machine cycle consists of 3 to 6 T states. Okay, now T state. Next, what is the T state? It is the time corresponding to one clock period. Okay, and the T test, that is the basic unit to calculate the execution of uh, of any instructions and programs in a processor. Okay, so these are the definitions you need to know. Next, move on to this next slide, which is the different machine cycles. So machine cycles means it is the time required to either accessing either the memory related operation or I related operation. Okay, so how many machine cycles are there? There are 5 machine cycles. Okay, 5 machine cycles: opcode fetch machine cycle, memory read machine cycle, memory write machine cycle, IO read machine cycle, and IO write machine cycle. So here T state, T state, it is the one clock period. Now combinations of several T states, it creates one machine cycle, and combinations of several machine cycles, it creates one instruction cycle. Okay, so these are interrelated. Uh, so here for every machine cycle, these are fixed numbers of T states. There are fixed numbers of T states. Now, opcode fetch machine cycle. So every instruction, it has some machine cycle, either one machine cycle or two machine cycle or 6 machine cycles, whatever. So opcode fetch machine cycle that will be processed by each instruction first. Every instruction uh, every instruction has first machine cycle, which is opcode fetch machine cycle. And for maximum number of cases it requires 40 states. So there are certain exceptional instructions, those are required, those have more than 40 states are needed to perform this opcode fetch machine cycle. I will discuss it another time. What are the different or exceptional instructions? Those are required more than 40 states to perform the opcode fetch machine cycles. But right now we have to remember that most of the instructions, 99% cases, all the instruction needs 40 states to complete the opcode fetch machine cycle. And every instruction machine cycle, first machine cycle will be opcode fetch machine cycle. Now, based on this opcode means which operation is to be performed. Based on this opcode, processor identified that whether it requires any other machine cycles or not. It may be it requires maybe this memory read cycle or memory write cycle, or both of them, or any one of them and other IO write cycle, maybe any machine cycle. It depends on after the completion of this opcode fetch machine cycle, which will be performed by every instruction initially. Okay, so for every instruction, first machine cycle will be always opcode fetch machine cycle, and it requires 40 steps. This type of 40 steps will be required. Means this one is 1T state, again this one is second T state, again 30 state, again 40 states. So it requires 40 states to perform one machine cycle. Which one? Opcode fetch machine cycle. 40 states are needed. Okay. So now the machine cycle description. So machine cycle. Now each instruction I have told you earlier that each instruction of the 8085 consists of 1 to 5 machine cycles, and instruction execution will have compulsorily the upcode fetch machine cycle, that will be the first machine cycle for every instruction. And then depending upon the instruction and instruction cycle, we'll have one or two or more than this other cycle in the list. So when the 8085 processor executes an instruction, it will need to access external memory or IO devices. In other words, it needs many machine cycles in a specific order. Okay. So the first machine cycle is opcode fetch machine cycle, which is here given in this picture, in this pictorial representation. Okay, it is a pictorial representation. So as per the definition of timing diagram, so timing diagram, it is obtained by drawing the binary labels on the various signals of 8085. Now these are the binary labels, 1 or 0. Okay, and these are the signals. So whose binary labels will be reflected in this pictorial representation? These signals. Okay, clock signal, the address, upper 8-bit address bus, lower 8-bit address and data multiplex address and data bus, ALE signal, the status signals, and the control signal read bar. Okay, or write bar, which one is required. So it needs these 5 signals to represent it in pictorial form, to reflect the binary labels of these signals. Okay, so if you so in exam you have to specify these signals in this way, and these are very important, because if any signal is missing, then full diagram will be wrong and it will be 0. So there will be no part marking. So you have to specify all of these 5 6 signals um, compulsory on this timing diagram. Okay, so opcode fetch machine cycle, basically this that is the first step in the execution of any instruction. Now in this cycle, what happens, the microprocessor reads the opcode of an instruction from the memory, because we know that every instructions are stored inside the memory. So from that memory, it reads that opcode, it fetches that opcode. Now the control and status signals for these machine cycles, IO M bar and S1 and S0, are in this way. it is given IO M bar 0, S1 equals to 1, S0 equals to 1. Okay, I need to share something. So processor status and processor status signals, what will be the status of each one? If you have pen and paper with you, we can write it down in this way, what which I have written over here. Is it visible?
Yes, sir.
Okay, so write it down as, if this one is 0 and S1 signal is also 0 and S0 is also 0, then what will be the processor status, your operation status? That will be in halt state. Okay, so the next combination will be, if it is 0, if this one is 0 and this one is 1, then your operation status will be called as memory write. Memory write. It is a memory write operation. Okay, at that time the signal level will be in this way. IO slash M bar will be 0, S1 signal will be 0, and S0 signal will be 1. And for the next combination, if this one is 0, next is, sorry, 0, 1, 0, then it is called as memory read signal. Memory read signal, or memory read operation. Memory read operation. If these three signals are changed in this way, the IO slash M bar is 0, S1 is 1, S0 is 0, then this is the memory read signal. Okay, and if this one is again 0, this S1 signal is 1, S0 signal is 1, then the operation is called as opcode fetch operation. Opcode fetch operation. Opcode fetch operation. Now coming to the next combination, which is 1, 0, 0. So again, if it is 1, 0, 0, the state of operation is called as halt state. Okay, so whether this signal is 0 or 1, whether this signal IO embed 0 or 1, if both status signals S1 and S0, if both are 0, 0, in these two cases, halt operation is performed. It is going into halt state. Okay, now if it is 1, again, the next combination is 1, 0, 1. 1, 0, 1. Then it is called, what is it called? Like if it is 0, 0, 1, it is called memory write. And if it is 1, 0, 1, then
Right. Data right.
hmm? So Bhagavas are either memory operation or IO operations there. If it is 0, 0, 1 means memory write, then 1, 0, 1 will be for which operation?
Right, sir.
Sorry,
IO right.
IO write. Good. IO write. Because already memory operations has been defined. Okay. So IO write. Okay. Next combination will be for 1, 1, 0. Now tell me.
IO read.
I read. Good. I read. Okay. The next one and the last one is 1, 1 1. Then it is called interrupt acknowledge. It is called interrupt acknowledge. Okay, if all signals are 1 1 1, it is interrupt acknowledge. So you have to remember this table when you'd like to draw the timing diagram of any instruction. You have to remember this table so that you can specify the signal levels if it is required for any operation status, any processor status. Okay, like for opcode fetch, every time this IO M bar signal will be 0 and S1 and S0 will be 1 1. Okay, so you have to remember this table. Is it okay? Have you written this one? Shall I stop the
Yes, sir.
screen sharing? Okay, so okay, so you can see it from here that in case of opcode, this is opcode fetch machine cycle. So at the opcode fetch machine cycle, what will be the combinations of these three signals? It will be 0 1 1. That's why it is written in this way. Okay, now this differentiates it from the memory read machine cycle. Okay, because not only memory read, for every machine cycle this combinations will be changed. Now for every instruction it has a 1 byte opcode which is stored in the memory. So uh, every instruction execution starts with opcode fetch machine cycle. Okay, and right now I would like to discuss about the signal, uh, how these signals are changed and what is the function of each one, each step, T1, T2, T3, T4, T state. I will explain it now. So listen carefully. So for output fetch machine cycle, we need 40 states. So the negative edge, falling edge of one pulse to the rising of next pulse is called 1T state. So this is T1 T state, then T2, then T3, and T4. Now my higher order address bus is looks like this one, and it going in this way. Lower order will be in this way. In between, it is a dotted line. Okay, in between this one is your dotted line. I think all of you can see it. Can you see it? This one here between this box and this box, the dotted line is there, and again the last portion of this one is again dotted line. Okay, ALE signal will be high for first T1 T state, and IOM bar will be transferred in this way, and read bar signal initially is read bar means whether so it's the active low signal. When this signal goes low, it is activated. When this signal is high, it is deactivated. So initially it is deactivated, but when this middle portion of T2 to middle portion of T3, it will be activated. Okay, and then again after that up to the last one, it will be deactivated. Okay, now the shape of these lines, it signifies that if your address is like 8000, 8000 is your first starting assume. Now, if it is converted into binary form, what will be the binary levels? 1000, 0000, 0000, clear? So in total 16-bit binary form, only one bit is your 1, that is high, another bits are all low, that is 0. So that 1 should be transferred through this line. It represents this line, and all other bits, those are 0, it represents this line. Clear? That's why it is given in higher and lower lines. So every signal, it is changed either 0 or 1 in this level. So that binary label is reflected in here in this position. Okay, that's why the signals are look like this. Now this cross section, so this cross section reflects these signals are activated or enabled after this position, and up to this one it has some mechanical delay. Okay, it has some mechanical delay. Why? Because as soon as any signal comes, it doesn't goes into stable state. It will not go into stable state. Okay, it takes certain amount of time. So that delay reflects over here, and after getting it stable, this position reflects in this crossover section. That means after this section, every signal goes into stable state, and that signal is taken as your actual input. Okay, because otherwise it will be taken as your inputs with noise. Okay. So that's why these crossover things are there. And now for any operation, any opcode fetch operation, opcode is stored inside any memory location. So first microprocessor needs to identify the memory location, and if it goes to such memory location, it can read the data from that particular memory location. So that's why initially when at T1, T2, T3, at T1 T state, the content of the program counter. So who gives this memory address? Program counter. Program counter will give the memory address from where the next instruction will be fetched. So the content of program counter is placed on this address bus. Okay, this is the lower order address bus. This is the higher order address bus. The lower order address is placed in the AD0 to AD7 lines, and the higher order address is placed in the A8 to A15 lines. Okay, the change of binary labels that is shown in the timing diagram by cross section, as I have told you earlier. And after that, IO bar signal goes low because at that time it is 0. So IO bar signal goes low, but S1 and S0 it goes high. That's why it is given in this way. Okay, so IO bar signal goes low to indicate that a memory location is being accessed, and this signal is used by external device to identify the memory and IO device access for interfacing. And these signals on the status lines is 0, S0 and S1 that are also changed to the labels as indicated in the last table which I have discussed you earlier. Next is the ALE signal becomes active high to indicate that the multiplex address and data bus are acting as the lower order address bus. So when address, according to this name, what is the full form of ALE? Address latch enable. Address latch enable. So when latch is enabled, address will be transferred. So when latch is enabled, the signal will be high. When latch is disabled, the signal will be low. And when latch is enabled, only address will be transferred through this address bus, lower order address and data bus. And when latch is disabled, the same line that will be used for data purpose. Okay, so that's why at every opcode fetch machine cycle at T1 T state, the ALE should be high always. When ALE is high, at that time address will be transferred through this address bus, and through this also this address bus is also used. And at that time the IO bar and S1 signals will be varied according to their status, and at that time no fetching operation is performed. That's why no read signal is activated. It is just give the address. যখন অ্যাড্রেস দেওয়া হয় তখন কিন্তু জিনিসটা রিড করা হচ্ছে না। ওকে, অ্যাড্রেস দিয়ে দেওয়ার পরে জিনিসটা ডেটাটাকে রিড করতে পারবে। So when this address is transferring, at that time no read operation is performed. That's why read operation signal is high, means deactivated. So when this will be activated? After getting the address through this address bus. So at T1, T2 T state, what happened? The multiplex lower order address bus is now changed to the data bus. So the lower order address bus in this bus is removed by the processor, and it takes certain amount of time, which is used for which is called as high impedance state. Okay, so this dotted line reflects the high impedance state. It is the changeover mode from the address bus to data bus. Okay, and this line is automatically in this order, that means these are not changed in any way, because these 8 address lines are specifically designed to give the address only. Okay, there will be no data. So this one has been changed to, if this one has been changed to data bus, at that time ALE signal goes low and it activates the read bar signal. Okay, the active low read bar signal is made low by the processor, and this signal makes the memory device load the data bus with the contents of the memory location addressed by the processor. So until it goes high again, the read operation will be performed. Okay, so when it goes low, read operation is started, and it is given in this way. So it reads the particular data, a particular contents of the memory location, because already address is identified. And how much time is required for this read bar signal until it gets deactivated again? The total read operation will be performed, and it reads the data and give it to the data bus. And when this bar then read bar signal goes high again, it is deactivated. Now it is ready for decoding and execution purpose, and that's why this dotted line is there and address line is unspecified, because at that time for decoding and execution purpose no address and data bus is required. It is already stored in somewhere else. Okay, that's why these are unspecified and this is used in dotted line. Clear? So so at T1 T state the address will be transferred. At T2 and T3 T state, the actual read content must be read by the processor, and at T4 T state, the decoding and execution, decode and execution operation is performed. Clear? So that is the opcode fetch machine cycle. So this type of representation will be for every machine cycle, whether it's opcode fetch or memory read, more or less same type of design diagram will be there. So opcode fetch machine cycle. Next is memory read machine cycle. Okay. Memory read machine cycle. Uh, Again, this every memory read machine cycle requires 3 T states. So T1, T2, and T3. And this one is higher order 8-bit address, this one is lower order 8-bit address, this is ALE signal, this is 3 control signals, and this is the 3 status signals, and this is the control signal, read bar control signal, because it's a read operation. Okay, so in the same way, so basically it is executed by the processor to read a data byte from memory, and instructions that are more than 1 byte long, more than 1 byte. All of you know that how many types of instructions are there: 1 byte, 2 byte, and 3 byte. So the instructions which are more than 1 byte long have the memory read cycle to read the second byte of the instruction after the opcode fetch cycle. After the opcode fetch cycle. Okay, and this will be same. The address must be transferred over here at T1 T state. When ALE signal goes high, at that time read bar signal is deactivated and IO bar S1 S0 signal will be changed according to the table which I have shown you earlier. So it will be 0 1 0. Then after T1 T state, for T2, when this ALE signal goes low, that means it is deactivated and is now ready to transfer the data, and using this same line for data bus, same line as data bus. And when this read bar signal goes activated, it is enabled, it reads the content from the memory location and it is send it to the through the data bus, and it is sent it and it is stored inside the instruction, any register, okay, as per your instruction execution. So this is the memory read machine cycle. Memory write machine cycle will be same except this one. At that time read bar control signal is used. Now the memory write control signal will be used. Okay, write control signal will be there, all others remain same. And another thing is the change of these three signals will be based on the table, the status. It will be 0 0 1. Okay, the working principle will be same. And I read cycle means those were for memory related operations. Now these are IO read and IO write. These tools are related to the IO related operation, peripheral related operation, input output device. So the same type of operation can be performed here. This one is your IO port address. um, the IO port address will be 8-bit in size, so whatever be the address over here, that will be reflected and just copied to the upper order also. Okay, suppose the address is 80, so 80 will be here, here also 80, which is just copied the lower order address bus at the upper order address bus for easiest designing purpose or interfacing purpose. Okay, the the status will be changed according to the table. 110 will be for IO read machine cycle, and that is the read operation, that's why read control signal is used. And if it is based on the write cycle, so write control signal will be here. Okay, so these are the machine cycles which are required to execute one complete instruction. Okay, so it may be required one machine cycle, or more than one machine cycles may be required for any another instruction execution. So it goes, it is related to the function of that particular instruction. Okay,